Welcome, I'm John Tull, Science Coordinator for the Great Basin Landscape Conservation Cooperative. For those of you who may be new to the LCC, we are a partnership among private and public groups working to meet large-scale conservation challenges across the 5-state Great Basin region. We've supported a variety of conservation projects on high-priority topics. This series highlights a few of these projects in addition to some projects like today's that we've been a supporter of as important research in the Great Basin. We hope that these webinars can provide a platform for discussion about the research and its application to the Great Basin. We will keep today's presentation relatively short, around 30 minutes, and then we'll reserve the second half of the hour for questions and discussions with the researcher and with Jon Sjoberg, a manager who's involved with the project. Since there are a lot of folks on the webinar, we ask that you type your questions as they arise. We'll read out your questions for the speaker at the end of the presentation. Today's webinar will be recorded and available on our website later this week, so if you have other colleagues or interested people, please keep an eye out for the announcement of the archive and you can send that along to them. So right now I'm going to point out how to use the Q&A feature. On your screen you'll notice that there's a small collapsed control panel in the upper right corner. By clicking on the small arrow button, you'll be able to expand that control panel. In the expanded control panel, you can send in a question by simply typing that question into the chat area and then pressing send. This question will be sent to us to respond to at the end of the webinar. So with that, I'd like to introduce today's speakers. As soon as I find the bio information here, forgive me. So Helen Neville and Jon Sjoberg are going to be giving today's presentation. Helen, as Director of Research and Science Partnerships for Trout Unlimited, works with TU colleagues and various collaborators to provide management-relevant science and increase on-the-ground capacity for restoration and recovery efforts on native trout. She completed her graduate work at the University of Nevada, Reno in 2003, using genetic tools that characterize population structure and dynamics in Lahontan cutthroat trout. She worked at the Rocky Mountain Research Station in Boise for 3 years as a postdoc, and then she was also using her genetic tools to address conservation questions in Chinook salmon and redband trout before beginning her current job with TU in 2006. Jon Sjoberg has a BS in Renewable Natural Resources from the University of Nevada, Reno, and over 35 years of experience in fisheries and aquatic species conservation. He's currently the Chief of Fisheries for the Nevada Department of Wildlife in Reno, and prior to that worked for 24 years in Southern Nevada as NDOW's Native Aquatic Species Biologist and Regional Fisheries Supervisor. So with that, I'd like to hand it over to Helen, who will give the presentation, and Jon will be presenting some information following that, and they'll both answer your questions as they come up.
Thank you, John, and I very much appreciate the Great Basin LCC giving me the opportunity to present this work because I think it's highly relevant to this geography and everything the LCC does. And I appreciate all of you taking the time to get on today. So I am just one part of a much larger team. This is a huge collaborative effort, and it really was the brainchild of Seth Wenger, who was a postdoc with Trout Unlimited, and he has since moved to the University of Georgia as faculty there. He's also brought on Doug Leisure as his primary modeling postdoc, and the two of them are responsible for the bulk of the population modeling that I'm going to talk about today. The other folks up in our office, the science office here in Boise, have been involved in a lot of the data acquisition and working with the partners and building the database that I'll be describing, as well as modeling a lot of the covariates or the environmental and biological other attributes that go into the model that I'll talk about. Erin Langoose is part of a larger project, and she does individual-based modeling, which I won't cover today, but she's part of this whole team. We also work a lot with Jason Dunham and Nate Sheldgren at USGS. Jason has a long history of working on Lahontan cutthroat trout in particular and all other hosts of salmon and trout and critters. And Nate has lended a lot of expertise on some of the modeling. Dan Isaac and Charlie Luce and others at the Rocky Mountain Research Station have been pivotal in providing the stream temperature models and the flow models that I'll talk about. And then finally, we work very closely with Mary Peacock at the University of Nevada. She and Jason and others had done a long-term population viability modeling effort in the early 1990s using a different approach that we've kind of used the data from to anchor this approach. And so she's lended a lot of data and expertise on Lahontan. So just quickly before I get into it, the funding, the bulk of this project actually has been funded over the past 5 years. This is our 5th year now of NASA funding, which is kind of interesting, and I'll describe why that's the case further on in the talk. But that provided the backbone. Trout Unlimited has provided a lot of funding in staff time. The Bureau of Land Management has given us funding, as well as Fish and Wildlife Service, and so all of those are direct contributors. A lot of my salary actually comes from the National Fish and Wildlife Foundation for our Lahontan Keystone Initiative. And then Seattle City Lights has funded Aaron Langoo's work up at University of Montana. But the idea of taking on this project, or our motivation, was really to try and move us toward better conservation planning. Managers of any species of conservation interest need to know things like which populations are most likely to persist, which would benefit most from what management actions, where could we reintroduce our organism and where might they be likely to persist in the future, and how might climate change affect populations, among a lot of other questions that we all ask. And so what we really want to be able to address these questions are quantitative estimates of population viability, or on the flip side, extinction risk, and I'll kind of talk about the two interchangeably, probably using the term extinction risk more frequently. And we'd also ideally like an understanding of the major drivers of population dynamics so that we can identify management opportunities. And this is not really just an academic exercise, it's something that we really rely on and need for defensible management on many fronts. This is just one example of the Arctic ring seal, which was petitioned for listing under the Endangered Species Act. And that listing was denied because they had very little data on the current population level, had little ability to project any decline in the population, and overall had no real background for defining an extinction threshold for that species. So because they didn't have this quantitative information, that potentially warranted listing was denied. So what we would ideally want in order to get to these quantifiable answers is to use something called population viability analysis. This is a very large field of science that got its legs really strongly in the 1990s. And the idea is that we might know enough about a given population to be able to kind of characterize it in various ways and the things that influence it, so that we could do these simulations over time. So here we have the population size on the y-axis, and we might initiate it at some given population size. And then we simulate the behavior of this population based on these other factors over time. And we see how often the population either persists into the future or goes extinct, like this red line. And so in this case, we had one extinction event out of 5 simulations. And so we would say we have a 20% extinction probability. In reality, when we do these models, we do hundreds of thousands of those kinds of simulations. But we don't actually use population viability in practice as much as we could. And that's because it's very data intensive. It takes typically 7 to 10 years of consecutive abundance estimates at minimum for each population. And typically that's not the way agencies or any of us do our sampling in the field, at least not across many populations at once. Typically with earlier approaches, including the PVA study on Lahontan I mentioned before, each population is modeled separately. And so that actually gives us limited options for extrapolating across populations so that we can understand the influences at landscape scales, which we know are important for these fish. In some of the earlier or alternative modeling approaches, like there are some packaged PVA model approaches, the parameters for those models, and by parameters, I mean the parts of the equation that you use to run the models that define or constrain or sort of define the behavior of populations. So you have to put in values for things like growth rates, population growth rates, or carrying capacity, which is kind of how many organisms you think can fit in a given habitat. And in these typical package modeling approaches, these values are taken from literature. They're not using the actual field data to be estimated within the model, but you initialize them from literature values. And so in practice, instead of quantifying PVA for populations, we often use surrogates or rules of thumb. In the fisheries world, a lot of us have relied for quite a while now, almost 2 decades, on an earlier effort for cutthroat trout, at least by Hildebrand and Kirshner, where they asked the question, well, how much stream habitat do we really need to ensure that populations will be viable into the future? And they came up with this metric of 5 to 25 was it 25 kilometers, depending on the habitat quality in these populations. We might also use something like land cover, land use, or climate vulnerability. And some of you might be familiar with TU's efforts in this Conservation Success Index, where we brought together the state agency and the agency data on various cutthroat trout species, and then paired that with climate metrics and land cover and vulnerability to things like energy development, and tried to do a comprehensive status assessment. But in all cases, we're really relying a lot on surrogates for viability that are not validated and often can't be validated as related to actual viability. So what I'm going to talk about today is a model that we've developed as an alternative approach. It is a multiple population viability analysis. It's a statistical model, and I'm not really going to talk at all about the statistics of it today. But some of the key attributes are that it does population viability on many populations at once. The models are fit using actual observations of organisms. So in this case, we use all of the available data across all populations simultaneously. And this simultaneous estimation lets us borrow information to estimate viability for populations with little or no data. So we might have some populations that have been very extensively sampled over the years, and others where we sample them once every 5, every 10 years, and we don't have much information. Well, by doing these models over all populations simultaneously and understanding what factors drive the dynamics of populations that are well sampled, we can start to fill in the gaps for these other populations. And so, this not only allows us to do estimates for other populations, but also to explore which variables across the landscape most affect viability. And so we can learn something and then understand better how to formulate effective management on the ground. So the advantages of our approach are that the models produce quantitative estimates of viability. This is what we really want. They also enable range-wide assessment of status. So also what we really want is to be able to look at all of our populations at once and say, what do we have across the landscape, and start to be strategic in prioritizing our actions. They use all available data, and I'm going to spend a little time on this in a minute. And collectively, these attributes let us test the effects of management actions. Another key is that this is actually not a fish model. We're doing it all in fish because we're Trout Unlimited, but it's applicable to any species with appropriate data. And by appropriate, I mean that our models are best suited for populations that are small or at least in isolated habitats. They don't work well for big networked interconnected systems, and that's where the previous researcher, Aaron Landgoose, up at the University of Montana, I mentioned, has been brought in to do this network simulation models. But our models are really for isolated populations, but those are the populations of key conservation concern. So we're applying the first part of our model. The grant that we got from NASA was to sort of show proof of concept, and we focused on Lahontan cutthroat trout for that effort. And so we're 4 years in, we've completed the final model for that. And the Lahontan cutthroat trout are ideal for this approach because they are listed on the Endangered Species Act, and so they're of high conservation interest. They're found mostly in small and isolated populations, so that's what suits our model well. They've actually been intensively sampled. There are tons and tons of data available for Lahontans, even though they haven't necessarily been rolled up before to do these kind of range-wide estimates of viability. The data are available, which was a tremendous resource. And I'll note again at the end that we're also applying these models to redband trout and to Bonneville trout, cutthroat trout. So just briefly to give you sort of a high-level overview of the way the model works, it's a 3-component hierarchical model. So there's 3 separate parts of it that feed into each other. So this observation model is where we use the field data. And with this, we all typically ask the question, how many fish are in the sites that we sampled in this given time period, this year, or whatever the time period may be? So this is just one example. Many of us go out and we have, either sites that we sample frequently or have different sampling schemes around the ranges that we work in. But in most cases, we have set and identified sample sites, and they might vary by size, that we often repeat in various sort of time frames over time. So we go back, and in fisheries, we go through these sites and we have the defined units. So we might block net both ends, the upper and lower end of the site. And we do what's called depletion sampling using electrofishers. So you put a small current in the water and that stuns the fish, and we're able to collect them easily that way and count them without hurting them. But the idea is we go through and we do one pass of the site. we take the fish out that we captured and hold them on the side. We do another pass and take those fish out, and then we do a third pass and take those fish out. And so over this process, you know, typically what you would want is that the number of fish across your passes would decline, because if you're doing a good job at catching fish, you should catch most of them in the first pass, and we use these patterns in estimation. So here we caught a total of 19 fish, which is information, but that's not what we really need. What we really need to know is how many fish did we not capture, so that we know both the observed or the caught number of fish and the unobserved or the number of fish that we missed. That is what our estimate is for how many fish were in that site. And in fisheries, what we use for this is a depletion estimator, where we look at the patterns of this decreasing capture over passes. And there are lots of little packages and other programs that use various statistical estimators of depletion, but they all often make very unrealistic assumptions. Things like that your capture probability, the likelihood of catching a fish, is exactly the same in the first pass as it is in the fifth pass, when we know that's not true. Once you go through and start zapping fish, they typically hide or move, and so that's not very realistic. They also don't often pull in site-level environmental characteristics. And so what Doug has done, which is a really nice part of this model, is that he's incorporated a data-driven site-level estimator of this capture probability and to estimate the total number of fish in each site. That also incorporates information on watershed size and flow, because those are two things that are very, very influential on how likely you are to catch fish, and also captures all of the error involved in this sampling. So we use, we can pull data into these models that are collected in various ways. You know, we've got a lot of different people contributing data that I'll show in a minute, but we all go out and sample different populations over different years. We might have some sites that we sample in one year, and maybe some of those sites we resample again in future years, but others are different, and that's okay. We can incorporate all of that information in these models. Some of us do typically do three or four pass, two to four pass sampling every time. Some of us do one pass sampling, and we have the ability to use all of that information in these models across all years, across all populations. So once we've gotten the field data integrated and have estimated how many fish were in all of our sites for this population in this time period, that gets scaled up to estimate the population size in this sampling model. So we take the information from all these sites, and then we know how big those sites are, and we know how much of the overall habitat, the distribution of the fish in the whole habitat, what percentage of that we actually sampled with our sites. And then we can ask the question, how big is the population here in this year? And then that gets rolled into this process model, which basically is estimating the viability or what happens to the population over time. Here's where, again, we use a lot of relationships with environmental and biological influences to predict how that population behaves over time, and I'll talk about that in a minute. So this is just an example. So we take the observation data, the field data that all of us are collecting, we roll that up, and we estimate population sizes. So here's one example of one population where we had 4 sampling events, or sampling years it might be. So we have 4 estimates of population size here, and these little whiskers are the error, the degree of certainty that we have about those estimates. And so what the process model does is it fills in the gaps around these estimates. So the solid line are the actual estimates of population size for all other times in the model. The little hatched lines here are the error around those estimates. And then we project that forward over a given period of time, and we get an extinction probability, how often these populations went extinct. In this case, this population probably has a very low extinction probability because even the error bars don't intersect 0 or whatever our extinction threshold may be. But you'd have other times where the populations kind of bounce around like this. So again, I said that one of the key attributes of this approach is that it's data-driven. So we have collected data from 1982 to 2016. And the reason for that time frame is that some of the environmental variables that I'm going to talk about in a minute, things like flow and temperature that we include in the model, the ways that we model them start in 1985. So we set a little lag in there with understanding what happened to populations before that, but that's the reason for that cutoff. So we have field data from the Nevada Department of Wildlife, Oregon Department of Fish and Wildlife, California Department of Fish and Wildlife, University of Nevada from that earlier population viability analysis, and then some of my own sampling studies on Lahontans throughout the Great Basin. we had to build a new database for this effort. Some of you may know for all the cutthroat trout across the West, there are usually status assessment databases available that the state agencies and Fish and Wildlife Service have developed, and they use those for their range-wide status assessments. But in those cases, a lot of the data gets rolled up into categories. So they look at things like population densities are framed in categories of 0 to 50 fish, 50 to 150 fish. And we actually needed, for our models, all of the individual data at a site level. So how many passes were done at this site, and what are the attributes of that site, and how many fish did you catch, and what were their sizes? So we had to go back and kind of compile all of that information anew, which has been that was about a 3-year effort to do that. It's been a great cooperation with the agencies, and I think we've gotten a lot out of this. But overall, it covers 232, I'd say, populations here, but in some sense, these are really waters because some of them do not have Lahontans in them. This includes the 69 formal Fish and Wildlife Service conservation populations that are evaluated now as high value for recovery, a whole host of sampling sites across the range, 34,000 Lahontan cutthroat trout, and including non-natives, over 45,000 individual fish have gone into this database now over all of those years. We also have gotten from the agencies all available information on eradications, or when they go in and try and remove non-native trout, and reintroductions of Lahontan cutthroat trout into the various waters. And importantly, this is a huge product of this effort. Like I said, this took 3 years, and it's the first time now that all these data, the detailed data, have been in a digital format and sort of archived in one place. So we've given this back now to the agencies. So NDOW has it, and they've agreed to host this and update it in the future so that all of us can continue to enter our field data every year, and we can continue to update these models. So obviously for fish in this dynamic habitat, environmental and biological characteristics are important and influence what happens to these fish. For these models, since they're landscape scale, we need metrics that are available for all populations and that are relevant to this fish. And in a lot of our earlier work, a lot of the early work that Jason Dunham did and Mary in that group and I did on Lahontan cutthroat trouts back in the 90s, we spent a lot of time going out and measuring things like stream widths, the number of pools, the depths of the pools, riffle pool ratios, woody debris, all sorts of metrics that we tried to relate to population variability. And they didn't really correlate to anything. They were not predictive of what happened to Lahontans in those sites or how many fish we might expect to capture. So we've really stepped back on a lot of fronts to looking at these landscape scale influencers. And so what we're looking at here is things like habitat quality, flow, obviously important to a fish, stream temperature, very important to cold water salmonids, and then fire and non-native trout, which are one of the biggest threats to the Lahontan cutthroat trout. And the nice thing is that many of these can be captured with remote sensing. And so therein lies the reason we were able to get this NASA funding, is that they have this program for ecological forecasting where they fund projects that help apply their satellite data to questions of ecology and conservation. And so we've been doing a lot of work and development on using satellite and remote sensing tools to apply to freshwater fisheries conservation and freshwater fisheries questions. And this is actually a really cool new review article that Dan Dowalter and Kurt Fessemeyer and Robin Bjork and Doug Leisure and Seth, the other parts of this primary team, have recently drummed up for fisheries. So this will be coming out in the next issue of Fisheries, and I think it's going to be a really nice go-to on how you can use these satellite and remote sensing tools. So just as an example, one of the metrics that we use to capture habitat quality is called the Normalized Difference Vegetation Index. It's a Landsat or satellite tool, satellite image that's available from 1985 to present. And what it captures is active photosynthesis and vegetation. And so you can see how this works, where in a dry year in a system, you can see that there's lots of this stream that doesn't have much photosynthesis going on or vegetation at all. And then the same system in a really wet year is very different. So we can capture differences over space and time with this, and things like, grazing, where grazing has really impacted large swaths of streams, it captures that as well. One of the other covariates that's obviously relevant to a cutthroat trout is stream temperature. And so for this is where we're collaborating with the Rocky Mountain Research Station, and Seth Wenger worked heavily with Dan Isaac to actually model a lot of this, but these are stream models that estimate annual estimates of mean August stream temperature for every 1 kilometer of stream across the entire West now. At the time we started this project, none of this was done and this wasn't done. So this is what we completed for this work so that we could use these covariates. And then since Dan has completed the entire Southwest. And these models measure or estimate stream temperature both currently and under future climate conditions. We also are using a flow model, the North American Land Data Assimilation System, or NLDAS, which I'm not really going to go into, but all of these models, as they get improved in the future, we can incorporate new models, updates, different models. So these are very flexible to use in the future, but this is what we're relying on now. Again, one of the biggest influencers on Lahontan cutthroat trout are non-native trouts. A lot of our systems in the east have brook trout, and then there are also rainbow trout and brown trout in other systems. So in most cases, we actually have data on these fish, and so we are actually using sort of rough quantitative estimates of what's going on with these fish. So you can see this is a population that had sort of a low level of introduction, and then all of a sudden kind of took off and invaded. So what we're doing is projecting forward right now using the most recent density as an influence on the population. So this is an example of the model output. So these are estimates for all of our Lahontan streams of extinction probability and extinction risk ranked in these categories by color to the year 2045 is what we're defaulting to now, but I'll show you how you can manipulate that and look at different time frames. Importantly, you'll see that a lot of these waters, like in the Ruby Mountains and then Sierra Nevada, that are in really good habitats, have 100% extinction risk. That's because there are not Lahontan cutthroat trout in those waters right now. Doesn't mean that they will not be viable in the future, but you can look at the impact of reintroducing Lahontans to these waters and how viable they will be in the future. But just as a note, when you look at these and are surprised that all of these nice Sierra streams don't have any fish in them, that's the state of where the fish are right now. So we also have the ability to use the models to look at management scenarios and ask questions like, what if we removed non-natives from all of these systems? What if we reintroduce Lahontan cutthroat trout to a given habitat? What if we remove fish from a founder population or source population to restore another population? What's the impact on that source population that we're removing fish from? What if we improve flows or reduce temperature through restoration or better grazing work? Or what if under climate change, these temperatures increase over time? So we've built a new tool to let users examine these alternatives. And how this works is the full model with all of the data and the population estimating and the environmental covariates are run externally, hundreds of thousands of simulations using this program called JAGS. And then we get the relationships from this full model that predicts the attributes of different populations and how they relate to environmental characteristics, and pull that into this little outside platform called Shiny Apps. It's a R package, R programming package. But what this does is allow you to do real-time simulations in this little external package that uses all of the results of these models, but applies the data and the environmental information from each of the populations you're interested in at a time. So I'm going to walk you through various ways to use this little simulator. So here's the website for it, and I'll show it again at the end of the talk. You should feel free to go and cruise around in here. So this is, the really nice thing is that it's Google Earth, Google Maps powered, so you can go in and just click on a population and then pull up all the information about that population. So this is Able Creek. It's a pretty small population, has an extent of about 7 kilometers. The estimated extinction risk to the year 2045 is 18% for this population. And then you can see that you can go in here and look at all of the available data. This is one of the populations that was included in that earlier viability study that Mary Peacock and others did in the late 1990s, early 2000s. So this is a population where we had a good chunk of data in certain periods. And you can actually go to the data tab and see all of the individual fish data for this population over time. You can also go to this habitat tab, and this is where you can see things like the presence of non-native fish. So Able Creek does have a little brook trout population in it that NDOW has worked hard to control over various years, more intensively here than more recently. But so we can model the impact of this level of density of brook trout on this population. You can also see the modeled flows, and again, this is specific to this population. You'll look at other populations up in the Rubies or the Sierras, and their flows are, I mean, their water temperatures are way down here, so different levels of temperature for each given population. And so this is the trajectory of temperature that's been modeled over the years. This is flow, specific to Able Creek again, and this is that satellite metric, the riparian vegetation, or NDVI, as estimated by satellite imagery for every year. The way we're forecasting right now, because this is a little bit more intuitive to us, is simply to resample the observations in the past years. So when we move out of the realm of 2016, we're resampling the observations in the past to look at the future, and I'll show you in a minute how you can manipulate that to ask different questions. So, okay, so Able has an extinction risk of 18%, and we know that there is a brook trout population in here. We can ask the question, well, what would happen to the extinction risk if we removed those brook trout? So you can go down here and see this little non-native trout slider, and right now it's set at the last observed density of brook trout in the system, and you can simply move that down to 0 and eradicate brook trout from the stream. And then we see that that reduces the extinction risk for this population. And again, this is based on the data from this specific population and the relationships of population dynamics with those environmental covariates that were derived out of the full model. So we can see that that does have an impact on the extinction risk, but we might want to ask the question, well, what happens with climate change? What if the stream warms over time? And so we can go down to these observed temperatures, and we can say, well, what happens if we think we'll observe in the future only the upper 50% of those temperatures, and slide this little slider up, and we can see that bumped the extinction risk up again now to 19%. So this really gives us useful information on what to think about, you know, what are the important things influencing these different populations. This is another example, Cottonwood Creek. It's in the Walker Basin, and it's a tributary to Walker Lake. You can see it has 100% extinction risk because it has been free of Lahontan cutthroat trout and any trout. This is actually on a military base, and they had chlorinated this water over the past decades to use it as a drinking source for some of their training. So the nice thing is we knew there were no trout in there. So it comes up as red, 100% extinction risk. But NDOW, importantly, reintroduced fish to the stream last year. And so now we can say, okay, given the attributes of this stream, how long it is, what the environmental variables are, and what we know about how populations respond to this type of environment across the range, what is the likelihood that that reintroduction will persist into the future? So NDOW, I think, introduced 250 fish to this. And so let's say, what if we assume 150 of those will survive into the future? We can go to this little reintroductions table and add 150 fish just one time, and you see that that population would have an extinction prediction of 5.4, a probability of 5.4%. So that's pretty good. That's quite a resilient population. Okay, what happens if we experience climate warming like we know we will over the future? What if, oh, one more thing I wanted to say, sorry, is you can not only look at the impact of reintroducing or supplementing Lahontans in a certain population, but like I mentioned earlier, you can also enter negative numbers here to look at the impact of taking fish out of a population to use them as a potential source for others. It's an important question to understand how that might impact other populations that could be at risk. So just FYI, you can just enter a negative number here. What if we want to look at the climate resiliency of this population? Again, we can go up to this temperature slider and move that up to whatever you want. Here again, I did 50%. So assuming that we're going to be observing the upper 50th percentile of temperatures, that population still has an extinction probability of 6%. So that's pretty good compared to what we saw with Able Creek, for instance. And that's really good information about the potential effectiveness of that reintroduction. Here's one last example. This is Little Jack Creek in the Maggie Creek Basin. So Maggie Creek has 3 main tributaries, Little Jack Creek, Coyote, and then Beaver Creek up here. And previously, all 3 of these tributaries were isolated from each other from these obviously impassable culverts. But in 2005, a bunch of partners came together and removed those culverts and replaced the overpasses with bridges and nice passage-friendly variable culverts. And Dan and Mary and I have monitored that population for quite a while, looking at both the genetic and the demographic responses to that, and have shown that fish now are actually moving among these populations, and that there's been a demographic boost, especially to Beaver Creek from this work. But what if we wanted to look now at how that reconnection might impact this population? Right now, we see that this small population, it's less than 5 kilometers long, has an extinction risk of just slightly over 20%, 21%. Well, what happens if we want to see what the influence is of fish moving in here every now and then? Again, we can go to this reintroduction tab and say, okay, given the variable flows in that system, I think it's probably reasonable to say there might be movement every 6, 7, 8 years. So here I put 5 fish 1 year, followed by 0 fish for 7 years, which means that we're looking at an infusion of 5 fish every 8 years. And you can see by doing that, it reduces the extinction risk to 8% for this population. So there are various ways to look at how movement and interchange among these different populations might help their extinction risk. So again, this is the website for the Shiny app, and as we update these models again in the future and have more field data going in, they will just get updated automatically. But this is the most current iteration of the model right now. Again, I think the important thing of this is that it's a really nice little exploratory tool that enables various users to go in and evaluate the efficacy and how much success they're likely to get from different management actions and make priorities at a landscape scale. We're actually now working on a batch capacity, so we're going to be building another simulator that you don't go in and click on each individual population, but we can ask large-scale recovery planning questions like, how does extinction risk change across the whole range or within this GMU that I work in if we remove all non-natives? Or how does extinction risk change range-wide if we experience X degree of warming across the entire range at once? And we're going to build in an ability to map those extinction risks out at large geographies like that. So that'll be done in the next 2 months or so. Again, it's important that these models can and should be updated with new field data on the fish, as well as the environmental influences as they come about. These satellite metrics and the flow models and the temperature models are always being updated, and so we can pull those in readily. We can switch to new models and better models as they come about, and we will be updating the fish hopefully on a regular basis. So right now we're working with partners, and Jon can talk about this a little bit, on planning for this collaborative need and funding for future updating of both the database and the models. And as an aside, we can talk a little bit in the questions if people would like, but this is obviously just a demographic model at this point. We don't have the ability to put genetic metrics in because we would need a genetic estimate for every population for every year across the whole range, which is obviously not available. But I am doing right now in the next year a range-wide comparison of almost all of the populations to update their genetic sort of extinction risk, and hopefully pair that and compare that to the outputs of these models in the future. And then again, just as a final note, we are completing these models in the next year on desert redband trout and Bonneville cutthroat trout. So we will keep you updated on that as well. So that's all I had to say. And now I think I'll let Jon take it away from there.
Jon, I think you might still be on mute.
Is that better?
Yep, now we can hear you.
Okay, I didn't realize that the screen was linked somehow to my phone because I'm talking to the phone. Apologies. Again, thanks, Helen, and thank you, Jon, and Great Basin LCC for hosting this. I just wanted to make a few comments, some narrative comments about really the value of this tool from a management perspective, both for future LCT management and also for recovery planning for LCT recovery. In terms of the management and recovery implementation part, LCT recovery is a really high priority, not just for NDOW, but for all the partner agencies. But one of the key issues with that is that all of us as management agencies are resource limited. So the ability to use this tool to help with prioritization, to help with focusing management actions where we can drive the highest benefits from various management scenarios to enhance recovery, to be able to maintain these populations on the landscape is really key. And there's a lot of things that Helen talked about, you know, in this model and in this the PVA that really are going to be useful, I think, going forward in terms of our ability to try to structure these management programs on the ground to really maximize those benefits. Being able to examine these different management scenarios and environmental variables and how our ability to either react to those or manipulate those over time is going to be important in identifying, you know, those locations, those populations, those systems where we can really have the highest effect. This idea of filling in the gaps, of being able to assess those relative benefits from restoration of unoccupied habitats, whether they're unoccupied by anything or occupied by non-native fish, and also being able to assess those impacts of translocation on donor populations is an important element in going forward and structuring these management programs. I think in terms, there's also a broader view here, which is these larger goals of recovery planning at both the range-wide and the GMU level for LCT. This is really good timing to have this tool available because we're in the process working with the Fish and Wildlife Service and other partners. We're just starting a process now to update that vision of recovery for LCT and updating those recovery goals and objectives. All of these elements that I talked about and that Helen talked about under management apply to things we're going to need to plug into that analysis and that understanding of what we can accomplish and where we can go in terms of having recovery goals and priorities that are really both effective for the species and actually able to be applied on the ground. You know, knowing what and where are the highest priority actions that will meet those goals of recovery, which is minimize extinction risk at both the range-wide and the GMU level, and also ensuring is the ultimate goal, getting to a point where the protection of the act is no longer needed for the species, is the direction we need to go. And having this ability to at least have this tool as a predictor and advisor to help us understand what these dynamics are in the landscape is going to be really important for that recovery goal revision process. There's some key future opportunities here that Helen mentioned. This network simulation model in terms of developing this batch capability in the population simulator so that we can better assess future scenarios at these larger scales is going to be really important for that recovery planning process. In terms of helping us to identify strategies that can maximize recovery benefit, not just on an individual stream or network stream basis, but really on the larger scale of the range of the species. There's a couple of things that Helen mentioned also I wanted to reemphasize. It's important to remember going forward that this tool is useful really only to the point that it can be maintained and updated with data entry and maintenance and managing these other parameters and updating the input so that we do get outputs that are as reliable as we can expect from this. She mentioned that NDOW is committed to hosting and updating that existing database for the fish data. That's something we'll be working on with TU. We're in the process of handing off that database now, and then working with the other partners, including both Oregon and California, on how we will maintain that in the future. And a key part of that we're going to be working on here this fall is developing an online access portal for field data that will allow direct update and entry of that field data by partner biologists for all the agencies in the 3 states. and it's been a pretty major effort, largely on TU's part, to assemble 30 plus years of data that ranged from reasonably usable databases to things that were in shoeboxes, and get them all into one coherent data set that allowed us and allowed them to build the PVA. So maintaining that going forward is going to be critical. But I think we're really excited about having this tool. It will provide us a lot of benefits in terms of being able to assess projected actions and get some additional comfort level on where we think we need to focus and prioritize those efforts, and hopefully continue to make some significant progress in LCT recovery on the ground. That's really all I had in terms of additional comments, but I think at this point we can turn it back over, and would be happy to address any questions or comments from anyone else that's listening on the webinar.
Great, thank you both. I'll go ahead and take over here for our Q&A session. So just as a reminder for those of you guys on the line, you can enter your questions in on your control panel. If you don't see that, obviously, you may need to look for the red arrow on the corner of your screen and expand that box there to enter your questions. And so far, we've got a few kind of clarifying questions that I'm going to start off with, and then a couple other more big picture questions that have come in. And so first one here, just a little clarification about Able Creek. Is that in the PFC? And I'm hoping you know what PFC stands for. And could it tell us?
PFC is a monitoring metric that BLM primarily uses in evaluating stream condition. So I'm not sure what you mean by is that in the PFC. I would think there are probably PFC data available for that stream at some points in time. And we have not, we've explored in other contexts using information like PFC to capture more localized influences of grazing and other things in redband and Lahontan cutthroat trout. But we're not able, unfortunately, to use that scale of data for these models because it would need to be available for every population across every year. And so that's what's limiting us from some of those more localized pieces of information where there's more intensive habitat modeling in some areas, but it's not being done in other areas. And unfortunately, right now, there's not an ability to pull all the data together on all of that monitoring across the range, but it would be a great thing to do in the future. So I don't know if that addresses that question or not, but happy to clarify again if needed.
Great, thank you. And if the submitter of that question has any follow-up, feel free to type that in. So regarding the online app, is there a way to get confidence intervals around the extinction rate estimates? And then also, can you tell us a little more about what the finest resolution you can attain with that is?
Well, the extinction estimates are a probability, so there isn't a confidence interval around that probability, but we can kick out estimates, and they're not shown in the Shiny app. But if you, I think Doug has different ways of looking. Hold on, let me see if I can go back to that. What you would look at here is this. So this shows you the estimate of the population size over time, and then the error around that population size, and then how, the downward trajectory here in terms of the more recent sampling that's been done. So that gives you an idea of where that population was and bouncing around, but the extinction risk is actually just a straight probability. And then the other question was about the scale of those probabilities.
I think this is more about the just resolution of the app in general. What was the finest resolution that you can attain?
Like spatial resolution. In this case, this is all at a population level. So, but again, it pulls in all the data here. This shows, the population estimate or the fish densities for this population in a given year, but that estimate is based on the raw data from every site that was sampled at that time period. But the extinction risk is given at the stream level based on the occupied amount of habitat in that stream.
Okay, thank you. And if there's any follow-up questions from those submitters, please feel free to type them in. So we have a question here asking, what kind of data and or models would be needed to apply this to other species, say pika, for example?
Right. Well, we've talked about that. That might be coming from Eric Beaver. I'm not sure. Yeah, pika actually would be a great species to look at this, because again, they're in isolated habitats and are not like strongly networked. So, I mean, what we would need is some semblance of population counts over various years at various levels, an idea of the size of the habitat, so the talus patches that they live in. And then, you know, for instance, some of Eric Beaver's work I know has been looking at temperature monitoring, both at using satellite scale efforts and also micro temperatures in each population. I mean, so there are various types of data. I mean, we can pretty much incorporate almost anything, I think, as long as it's available across the entire landscape across all years. And it's something that we've really explored, is trying to apply these models to pika. Obviously, that's kind of out of my purview at Trout Unlimited, but it's something that I know Seth and some of the others are interested in pursuing in the future.
Great, thank you. And what would need to be done to add potential recovery streams into this model to assess them in the future? Yeah,
that's a really good question. So that's where we, hold on one second. We actually are doing that. All of these streams, let's see, what do I want to go back to? All of these streams, these are all, this includes all of the potential recovery streams. So for our models, we basically included all waters that had an observation of a trout after 1985, and then we went back and mined a lot of Jason Dunham's earlier database that he had compiled for some other things at patch levels to look at observations of Lahontans and other trouts much earlier, back to like 1955. So we included a lot of these waters. A lot of these do not have Lahontans in them now. Most of these in the Sierras are not occupied, but we modeled those waters. So that's why I was saying when we have 232 populations, a lot of them really are waters. So these are within the historic range, not currently occupied by Lahontan cutthroat trout, or at least not a conservation population, may or may not have non-natives, and all of them could potentially be considered at various levels for recovery. We also, after we included our initial swath of populations, we went back to the agencies and loaded up these maps and said, okay, here's what we're including for potential future recovery. Anybody that has any other waters they want to consider or want us to have in the model, please let us know those and give us your sort of delineation of the habitat, and we will include those. We need to have them all in the model effort because we need to be able to model the covariates for all of them when we update these models. So I think we're reasonably comprehensive, or at least this has involved feedback from all of the agencies at this point on all the waters that could be potentially considered for recovery.
Great. I've got 3 more questions here that have come in, so we'll try and get through these as best we can. This next commenter is saying that they work with a species that is a metapopulation the species is metapopulation distributed, but not necessarily as patchily distributed as needed to use MPVA. And how would one assess the applicability of this tool to specific species distributions? You know, is there any publications that you know of that address this?
It's a really good question, and you know, it's something we've grappled with a lot, is how to look at dynamics of movement among these populations. And since this is a statistical model, we simply can't do that with this approach. That's where the woman Erin Landgoose up at University of Montana, that's why she was brought in initially, was to help with some individual-based simulation modeling. So we've actually done some of that modeling on, for instance, the Marys River here. She's got this program called CD Metapop that is a individual-based model where you can pull in different layers of, you know, stream temperature, flow, and all that kind of stuff, and model individual movement among these different sort of networked populations over time. But unfortunately, we cannot really look at that with this model. So that's why we're really focusing here on the sort of smaller isolated populations. But things like, you know, trout in a lot of cases do have migratory life histories, and a lot of other organisms have, you know, extinction colonization dynamics and things, but we're not able to look at that here. Although we do have some areas where the fish has gone extinct, or, you know, we can look at reintroductions and look at the viability of those. We do have one publication that's, I think, pretty much accepted now into biological conservation, and that is the initial modeling paper that does not talk about this large broad-scale effort and include the covariates or anything, but is the basic just backbone of the model itself, and then comparing it to the earlier PVA work that Mary did, just to sort of demonstrate the utility of this simultaneous approach. And then we have another manuscript that we're drafting on expanding that approach and then incorporating the covariates, and then we're going to have a third manuscript that I'm supposed to be working on right now, and we'll get done shortly, to apply it to Lahontan cutthroat trout. But the initial sort of verification of this modeling approach and the scientific integrity of it should be coming out in biological conservation.
Great, thank you. Another question here is, how often does a population need to be sampled to have reliable data for the model?
That's another great question. Actually, I didn't mention that in this. This is something that we're looking at right now. So the cool thing is, now that we have this model framework, Doug is working on going back in and saying, okay, well, what do we need as a sampling design? And, you know, this has been brought up by the agencies, that it would be very valuable for them to know what is the most effective sampling design to get the best and most accurate estimates of extinction risk. So he's playing with that right now, and I'm hoping we're going to have that guidance in the fall for Lahontans, and then it's something that we'll be doing as well as we expand to these other species. But we should have the ability to say, like, you know, how often do you need to sample all these populations? Do you need to anchor with a certain number of populations that you sample every year for a given amount of time? How many of those do you need? Or is, you know, sampling a population every couple of years okay? Do you rotate across all populations? Do we always, you know, how much multipass sampling do you need? Those are the kinds of questions we're going to be exploring this fall.
Great. We have one more question here, and then I think John Toll has some closing words for us. But this last question, so the asker is saying that the quantity and quality of water in streams is critical to establishment and maintenance of the fisheries, and getting streams into PFC and the reestablishment of beaver in the system is an excellent way to achieve these objectives. And the question is, what is being done to help Lahontan on the ground improve?
That's a great, yeah, it's an absolutely great comment and true. There are a lot of situations now where there have been some really productive collaborations. You know, for most of the streams that I work on in the east, I would say one of the biggest habitat impactors is grazing and mining, but a lot of our streams really are still being impacted by cattle. And so we do have some really nice examples, though, like in Maggie Creek and in the neighboring watershed Susie Creek, and then in the Rock Creek Basin, and up in the Trout Creek Mountains, McDermott Creek and Willow Whitehorse, where there are collaborative groups of ranchers. There's also this other group called the Shoesole Group that's on Redband just over the state border. In all these cases, there are very conscientious ranchers that have been doing a lot of work to try and improve their grazing practices. And that is one of the things that we can model very, very readily with these satellite tools, actually, is looking at the impacts of those. And we've seen some really great improvements. Beaver have come into a lot of these places, and as you noted, have increased the ponding and the water retention. And there's all sorts of cool work and documentation being done about that across the range, but we do need more of it.
Well, thank you very much, Helen and John. This is a great example of where science can really come into play for very, you know, clear management use. And, you know, we at the LCC are really happy to be able to showcase this work. I want to thank everybody who attended today's webinar. Again, the recording of the presentation will be available on our website later this week. If you have any additional questions that weren't answered about either the LCC or this research, please feel free to contact myself, Helen, or John, and our information is on the screen right now. Also, join us again for our next webinar that's going to be on October 11th at 10 a.m. Pacific, when Erica Fleischman will present on relations of cheatgrass-driven fire, climate, and birds in the Great Basin. Last but not least, we really want to know what you thought of today's webinar. So please take our short 2-minute survey that will appear on your screen as you log off. Your feedback is really useful and valuable to us, and it helps us improve our future webinars. So thank you again, everybody.